3 years ago, we dedicated ourselves on the single greatest endeavor in the history of our company. We decided to be all in on AI. We decided to be all in on HPC. That for the first time, we would design a GPU architecture that is dedicated to this field of work, dedicated to accelerating AI, dedicated to accelerating deep learning. And to do it, create it in a form factor, in an architecture that is perfect for high-performance computing. Several years ago, thousands of engineers got together. Approximately $2 to $3 billion of R&D later, we have built the most advanced processor, the most advanced GPU that I think anyone has ever undertaken. Ladies and gentlemen, the work of thousands of engineers, the most ambitious project we have ever undertaken, the Tesla P100. This processor is utterly amazing. The processor itself is over 15 billion transistors. 15 billion transistors. It is the largest chip that has ever been made. But it's housed on chips stacked on top of chips in the 3D stacking technology. And altogether, this module is 150 billion transistors. Now, just to put in perspective, what I was holding up just now, what was called GM200 internally, the Maxwell, the high-end Maxwell, 7 billion transistors. 150 billion transistors on this module. The odds of it working at all is approximately 0. 150 billion transistors, 5.3 teraflops, 64-bit double precision, 10.6 teraflops, 32-bit precision, and one thing that we did that I'm so delighted about, adding new features and new architectures and new instruction set formats for deep learning, 16-bit performance, 21.2 teraflops. Not only that, we increased the size of the memory internally. The amount of data that's coming through, pumping through our chip is so great because we're processing it so fast. 14 megabytes of shared memory register files. These are register files. This isn't an L2 cache. This is a register file. 14 megabytes of register files with an aggregate throughput of 80 terabytes per second on the chip. Utterly amazing numbers, amazing throughput, and on top of that, it has a 4 megabyte L2 cache. The Tesla P100, ladies and gentlemen. The thing that's really, really amazing about the P100 is that when we first started working on it, we have rules in our company. And in order to be successful in execution repeatedly, once after another, you have to be thoughtful about the amount of risk you take. And the reason for that isn't because you don't want to take one giant leap, and the reason for that is because by taking a lot of leaps over a long period of time, it is the best way to stand on the shoulder of giants. However, because this is such an incredible endeavor and we're changing so many things, so many new pieces of technology have to come together. We have a rule inside the company. No great project should ever endeavor 3 miracles. No project, no box, no chip, no effort should have to rely on 3 miracles. The Tesla P100 is 5 miracles. 5 miracles. First of all, the Pascal architecture. You guys saw some of the stats. This is also our first unified memory. So CPU and GPUs for many programmers in the audience. This is just it's got to be, wow, Christmas in April. Okay, this is so great. Unified memory, CPU and GPU can share memory. Preemption. Such a vital thing for a first-class computing processor. Now we can run very, very long programs and preempt the GPU. Preempting thousands of processors is no easy task. Preempting one processor is not so hard. Preempting thousands and thousands of processors at the same time, incredibly hard. Well, that technology has taken us a very long time to invent. Ladies and gentlemen, Pascal has preemption. I am so freaking excited about it. Are you allowed to say that on stage? That's how of a big miracle it is. Not to mention all the deep learning algorithms that it encapsulates. This processor has so many transistors, it runs so fast that unless we can figure out a way to reduce the voltage all the way to nothing, you simply are not going to be able to make this processor run at all. So we use FinFET technology. This is the world's largest FinFET chip that has ever been done. 600 millimeters squared. If I were holding it up right now, you could see it from the back row. This chip is huge. 15 billion transistors, incredible amounts of memory, all in FinFET, three-dimensional transistors. Not only are the gates three-dimensional, not only are the transistors three-dimensional, the chip itself is three-dimensional and is stacked on top of other three-dimensional chips. It's chip on wafer on substrate. The largest CoWoS chip that has ever been made. Integrated with HBM2, the fastest memory ever been made. There are 4,000 wires. 4,000 wires. Maxwell has 384. There are 4,000 wires that connect Pascal to all the memories around it. The processor is so fast, and we wanted it to be even faster. We wanted to create a multi-GPU configuration. That is the fastest you can imagine. And the processor is so fast, the communications between them, because they have to synchronize information, has to be just as fast. So we created a brand new interconnect called NVLink. 160 gigabytes per second. 5 times the speed, aggregate bidirectional speed of PCI Express. These miracles, every single one of them, are the first of its kind, and surely the first of its kind for us. Several thousand engineers worked all over the world together to bring it all together. And yet there was one miracle that we had no control. Well, I would say we have no control over any of these miracles. So many of this requires the partnership of great companies all over the world. TSMC, Samsung on the memories. Right? So many people were involved in this project. And the last miracle, we went all in on a brand new GPU architecture. But unless great AI engineers and great AI scientists were able to create new algorithms that could take advantage of it, we have just created the world's most expensive brick. And so this is such an important thing. 3 years ago, when we went all in, it was simply hope and faith that if we don't build it, they can't come. But if we built it, they might not come. And that, I think, is the courage of innovation. That is one of the things that I'm most proud of NVIDIA, the fact that we are willing to go all in on something, on sheer belief, with so much uncertainty. These 5 miracles came together. The odds of any of the miracles happening was relatively low. When you compound it into one project, it is practically zero. And yet, ladies and gentlemen, I can tell you, Pascal, P100, it is in volume production today. We took giant leaps in just about everything. Compute, bandwidth, GPU compute. And we've been working with developers all over the world, pioneers who are working with us, advising us along the way. And they just saying amazing things. Jan LeCun says GPU acceleration has accelerated the progress of AI. And that we need more GPU, more memory, more bandwidth, and Pascal is the ticket. John Kelly said this is a new era of computing. Andrew Ng says AI computers are like space rockets. The bigger the better. Pascal's throughput interconnect will make the biggest rocket we've seen yet. And Microsoft is developing not just a 158-layer network, they're developing a 1,000-layer network. Servers are being built by OEMs all over the world now. IBM Enterprise, Hewlett-Packard Enterprise, Dell, and Cray. They all have samples. They're building their servers. They will probably announce it in Q4. They'll ship it in Q1. However, between now and then, hyperscale companies all over the world are going to consume everything we can make of Tesla P100s. We are in production now. We'll ship it soon. And it will show up in the cloud first, and then by OEMs in Q1. So ladies and gentlemen, Tesla P100.